Hey everyone, how's it going? Hey Cleo, hey Tens. What have you all been up to? Has anyone been up to anything interesting? Found a way to spend our weird time? Just chilling. Yeah, that's as good as any way. Should do more of that. Grinding physics. That's that's already two very different vibes. Renovating our record shop. Whoa, this is such an eclectic mix of stuff. Damn. All I did was cut my hair. It was a bit of a. It's gone kind of well because the front is okay. The back is madness, but luckily you can't see the back. Electricity, which talks about EMF. Oh yeah, the EMF stuff is nasty. Maybe we'll get around to having a YouTube class on it at some point. Hey Ross, how's it going? Yeah, it will do. Used a beard trimmer and a pair of like standard like kitchen scissors. It's better than it was. I look a bit less mad. Cutting your hair today. Okay, well, has your mum cut your hair before? Or is this going to be like first time? Do you know what you're in for? First time. Have you been informed there's no option? Like you're not allowed to keep it long then? Yeah, mine is kind of like an under bowl cut. I just kind of beard trimmed the sides until it was like nothing there. Yeah, there's no barbers, exactly. But I couldn't even see the back. Yeah. It's quite something. Cool, let's see where we're at. I'll give everyone one more minute to arrive. Ah, cool. Yeah. Good. Okay. So, well, let's get ourselves started for today. So today is all about work and power. Funnily enough, actually, just on SnapProvise, I just did a web class on work and energy. So if you're at that, this is a really nice follow-up because we can go through some more exam questions. Anyway, in general, we have a load of exam questions to go through on work and power. Great. So as always, there's a coupon code at the end for SnapProvise. So stick around to the end and we can give you a coupon and you can try out SnapProvise for yourself and see what you think. Great. Okay. So let's just slam in and have a go at some questions. Let me know if you have any questions about the questions or about the answers to the questions, or if you have any answers to the questions. Cool. Okay. So we start with question 15 of some paper from some time. That wasn't very neat at all. Okay. The photograph shows a lawnmower being used to cut grass. Great. AI, in order to push the lawnmower, a minimum force of 650 newtons must be applied to the handle of the lawnmower at an angle of 42 degrees to the horizontal. Always just draw on the diagram any information you get. It just means there's less stuff you have to keep in your head at once. Okay, show that the horizontal component of the force is around 500 newtons. So how do we find the horizontal component of this force? They're pushing this handle in here with some force, aren't they? Equal to 650 newtons. How do we find a horizontal component? Good, we use trigonometry, SOHCAHTOA. Which bit are we using? I'm seeing some causes. This sounds good to me. Okay, so what's our triangle here? It's this right angle triangle here, isn't it? Good, okay. And we're being asked to find the horizontal component of the force. So that's this bit here. Okay, so what does cos say? Cos means cos of theta is equal to, wait, SOHCAHTOA. Oh dear. Okay, so K says adjacent over hypotenuse is equal to cos theta. So we're interested in this adjacent to this angle. So you're right. A is equal to H cos theta, which is equal to, what's the hypotenuse? That's this main force, 650, multiplied by cos of 45 degrees, 42 degrees even, sorry. And you should find this implies that A is going to be equal to roughly 483 newtons. So did everyone get something like that? Good. I'm seeing a 480, a 483 even. Good. Okay, and that is indeed about 500 newtons. So it looks like we probably got that correct. Good. Okay. So next bit of the question. The lawnmower is used to cut 15 strips of grass, each 7 meters long. Calculate the work done by the person pushing the lawnmower. Okay. So first of all, what's the formula for work done? It seems like we're going to need that. Good. Okay. So work done is equal to force times distance. Which force and which distance? Let's say I have some force and I want to know how much work is done. What's this distance? Or let's say we know the distance, in fact. That might be a nicer way of thinking this one. Is it just any old force? Is the work done by this force here when it moves this thing by some distance d? Is the work done equal to this force times the distance? Good, yeah. So there's two ways of thinking about this. You either find the distance that's been moved in the direction of the force, or you can find the component of the force that's in the direction of the motion. So we can get away with just using the horizontal force here. Absolutely right. Good. So let's write that explicitly here. Work done is equal to force in direction of motion times distance moved. So the force in the direction that this thing moved, it didn't lift up off the ground or go into the ground. The force in the direction it moved is, well, it's this 7 meters. Sorry, the distance is the 7 meters. The force is just the horizontal bit, the force in this direction. And luckily, we already calculated that. It was 483 newtons. So the work done is equal to 483 newtons multiplied by the distance moved, which is 7 meters. If you plug that into your, aha, and there's something missing here. What have I missed? This would be for what? This would be the work done for one of these 7-meter long strips. But they've done this 15 times. Good, absolutely right. So there's an extra point here. So each 7-meter strip, we're going to do this much work, but we've done it 15 times. So the total work done is this times 15. And that should be equal to 50,715 joules. Good, absolutely right. Got to do all of these strips. Okay, next question then. From question 15 to question 1. So, sail systems are being developed to reduce the running costs of cargo ships. Okay, so the idea here is that they, rather than just using some kind of an engine, they're also using some sail to take advantage of the wind of it. The sail and the ship's engines work together to power the ship. One of these sails is shown in figure 1, putting at an angle of 40 degrees to the horizontal. Okay. The average tension is 170 kilonewtons. Always sketch this stuff on the diagram. Show that when the ship travels 1 kilometer, the work done by the sail on the ship is this much. Okay, so what was that formula for work done? How are we going to do this? What do we need to find? It's kind of similar to the last question. Good. We just need to work with the horizontal bit of this tension, because that's the bit that's in the direction of the motion. Now it's moving 1 kilometer in this direction. Okay, so we need to find that horizontal component. So work done equals force times distance, where this is the force in the direction of the motion. So we need 170 times 10 to the 3. That's this force here, multiplied by cos 40 to get just this horizontal component, multiplied by the distance traveled. Good. Okay, if you plug that all into your calculator, you should get, let's see, do we agree with this? Yeah, this makes sense. You should get 1.302 times 10 to the 8. Times 10 to the 8. And what's the units here? Well, they gave us the units here, actually, didn't they? The units are joules. Fantastic. So you're absolutely right. We can use trigonometry to solve this question. Next, with the sail and engines operating, the ship is traveling at a steady speed of 7 meters per second. Calculate the power developed by the sail. Okay. So far we've been talking about work done. And work done is all about energy being transferred from one form to another. Here we somehow now need to go from talking about energy over some distance to power. Nice. So I'm seeing some good ideas here. Power equals force times velocity. Cool. Now, if I want to use this power equals force times velocity, bearing in mind that this is kind of very similar, well, in fact, you can understand this is coming from the equation for work done. Work done is equal to the energy transferred, but work done is also equal to force times distance. So then power is energy over time, which is force, distance over time, which is force times velocity. So this formula makes sense. Except here, when you write down this formula here, what force did this need to be? This isn't just any old force. It had to be this force. Yeah, it had to be this force in the direction of the distance. So you have to be wary of the same thing when you use P equals FV, because it comes from this formula. So you're right, power equals force times velocity. Which force? The force in the direction of the velocity. Good. So the velocity, of course, is in the direction of motion. So we just need to be using that horizontal force again. So that horizontal force, I don't remember, what did we say it was? It's 170 kilonewtons times cos 40. 10 to the 3. So it's 170 times 10 to the 3 multiplied by cos 40. So P equals FV also needs us to use the right force. Okay, and then we multiply by the velocity, which is 7. If you plug this into your calculator, you should get around 9.1 times 10 to the 5. Times 10 to the 5 what? 10 times 10 to the 5 watts. Good. Okay, because watts is joules per time. Okay, next question. Calculate the percentage of the ship's power requirement that is provided by the wind when the ship is traveling at this speed. The power output of the engines is 2.1 megawatts. So what do we think here? Has anyone got any ideas? We're being asked to calculate the percentage of the ship's power requirement provided by the wind. So we need the power due to the wind. If we want to just write this out as maths a bit more, power due to wind as a fraction of total power required, and then multiplied by 100. That's how you'd calculate a percentage. Do we know the power due to the wind? And do we know the total power output, the total power required? Let's take a look back through this question. The sail and ship's engines work together to power the ship. Let's assume it seems reasonable to imagine that the sail and ship's engines together are providing exactly what is required. They're providing exactly the power requirement. So I think if we take the power of the ship and the power of the ship's engine and the power of the sail together, that's probably the total power requirement. Now, what's the power due to the sail? The power due to the sail is this bit here, 9.1 times 10 to the 5. So what I'm saying is the total power is equal to the sail power plus engine power. What's that equal to? Well, we calculated the power due to the sails, 9.1 times 10 to the 5. Plus, what's this engine power? Well, we were told this. The power output of the engines is 2.1 times 10 to the 6. So power due to the wind, by which we mean like the power due to the sails, divided by this total. Okay, so what we want is 9.1 times 10 to the 5. That's the power due to the sails, divided by the total power that we're using, which is the sails plus the engine. And then multiply by 100 to get a percentage. Yeah, exactly. Both of them together. Good. Okay, so if we plug this in, what we should get is around 30%. Good. Okay, so that's our answer. The percentage of the ship's power requirement that's being provided by the wind is around 30%. Good. Okay. So next question. A cyclist pedals downhill on a road as shown in figure 1. From rest at the top of the hill, and reaches a horizontal section of the road at a speed of 16 meters per second. The total mass of the cyclist and cycle together is this much. Okay. Calculate the kinetic energy of the cyclist and the cycle on reaching the horizontal section of the road. So what's the formula for kinetic energy? We're going to need that to calculate this. Half mv squared. Good. And that looks like it's enough here. Half mv squared. That's the kinetic energy. Okay. Now what's the mass? The cyclist and the cycle. The cyclist and the cycle have this much mass. Okay. So times 68. On reaching the horizontal section of the road. When they reach the horizontal section of the road, they have this speed. Great. Okay, so this is the speed at the right point. If we plug all of this in, absolutely right. This is a nice, easy question. So this is going to give us 8,000. This should give us around 8,700. Well, it will give us 8,704, which is around 8,700 joules. Good, 8,704. Perfect. Okay, so let's see what comes next. The height difference between the top of the hill and the horizontal section is 12 meters. Calculate the loss of gravitational potential energy of the cyclist and the cycle. So how can we do this bit? What's the new formula that we need? Good, so change in gravitational potential energy is equal to m times g times the change in height. So we know the mass, we know the gravitational acceleration, and we know the change in height. So I think we've got it all down. 68. Again, yeah, cyclist and the cycle. Together they weigh 68. We don't know anything about either of them on their own. Times by change in height, which is 12. Good. Okay, so if you plug this in as well, you should get around 8,005 joules. Would it be minus 12? Yeah, so you're right. It would be minus 12, but they've asked us to calculate the loss. And so I think it's fine to say that they lost some positive amount of energy. So yeah, you won't be penalized there. Okay, 8,005 joules, right. 8,005 joules. What do we get for the kinetic energy? 8,704 joules. Interesting. Okay, so you're absolutely right. This is our answer. Now let's look at the next part. The work done by the cyclist when pedaling downhill. Yeah. What's weird about this so far? Did anyone kind of expect them to be the same, maybe? But that's exactly the point. It's not quite the energy, that kinetic and gravitational potential energy, just those two on their own must be conserved. It's that all energy altogether must be conserved. So there's probably some other energy transfers going on. Yeah, so friction sounds like it could be around. There could be some other stuff going around. So friction is like from contact with a surface. And there are other things that could be resulting in this. Also, I mean, actually, what's even weirder, though, is the kinetic energy is bigger than the potential energy. Look, they lost this much energy. They started off at rest, but they ended up with a kinetic energy bigger than the gravitational potential energy they've converted. So actually, none of this explains the weirdest thing, which is that they seem to have gained energy. So you're right, guys, that stuff will matter, but something even weirder is happening. There's a word in bold here that explains this. Can anyone explain this effect by rereading this question? Pedals. Yeah. So this person isn't just letting themselves fall from rest. They're also pedaling. Yeah. So this is really important. What kind of energy transfer is happening there? Yeah. So this cyclist here themselves is also creating some kind of an extra force. Or if you want to think about energy transfers, yeah, where's this kinetic energy come from? What store of energy is this human using that they're converting into kinetic energy? Yeah, I think they're converting a kind of chemical energy. They've got energy in their body. They've eaten some food. They feel in a good enough mood and they feel energetic enough that they can start pedaling on a bike. Yeah, it's come from their body. It's kind of a chemical energy. Okay, so actually the next part of this question addresses all of this. The work done by the cyclist when pedaling down the hill is 2,400 joules. So this is the work done. This is this extra energy transferred as a result of them pedaling. Account for the difference between the loss of potential energy, the gain of kinetic energy of the cyclist and the cycle. So, what do we want to say? Well, what would I describe work done as? How do you mean? So also I'll say in the meantime, so first of all, we're basically being just asked to discuss some of the differences between the different energies going on. So first of all, basic thing, because they're just asking about why is there a difference between GPE and kinetic energy here. So first of all, from what we've been saying, why is kinetic energy? Kinetic energy is actually bigger than initial GPE because why? So work done is force times the distance traveled. Yeah, but here's the problem. According to the question, the work done by the cyclist was 2,400 joules. So they put in even more. So you're right. Okay. So the kinetic energy is bigger than the GPE because cyclist put in extra 2,4 of work by pedaling. Now, here's the problem. Now we have to explain something else, which is why is it that the kinetic energy is less than GPE plus work done? There's all the energy that got put in. But actually, if you add 2,400 to the GPE, you get like 10,000 or something. Whereas here, the kinetic energy we get out is a measly 8,700. So then the other stuff that you were all telling me becomes important as well. So the other stuff you were all telling me was that energy gets lost in various other places. So kinetic energy is less than gravitational potential energy plus work done because some of the energy put in is converted into heat, or sound as the cyclist does work against friction and air resistance. Good. Good. There's these forces acting against the motion, things like friction and things like air resistance. And these cause us to lose some of our kinetic energy. Good. Well done, everyone. So, next question. It has been predicted that in the future, large offshore wind turbines may have a power output 10 times the largest ones currently in use. This would indeed be great. These turbines could have a blade length of 100 meters or more. A turbine such as this is shown in figure 8. Think about that, 100 meters. Like if you think about like a running track, it's like one length of a running track is just a blade on this thing. Okay, a turbine such as this is shown in figure 8. 7.8. At a wind speed of 11 meters per second, the volume of air passing through the blades each second is 3.5 times 10 to the power 5. Okay. So, AI, show that the mass of air that would pass through the blades each second is about 4 times 10 to the power 5 kilograms. So what do we need here? We've been told to find a mass. What kind of quantities have we been given? Good, we've been given a density and a volume. Fantastic. So what's the formula relating them? And in fact, I'm seeing it in the chat here. Fantastic. So density is by definition mass per volume. So the mass is equal to the density times the volume. The density we've been told is 1.2. And the volume we've been told is 3.5 times 10 to the 5. Times 10 to the power 5. So if you chuck all of this into your calculators, you should find 4.2 multiplied by 10 to the 5. And that is indeed about 4 times 10 to the 5. Perfect. Good. 7AII. Calculate the kinetic energy. Sorry, 1 second. Calculate the kinetic energy of the air that would enter the turbine each second. So we know what mass enters the turbine. We want to know the kind of quantity of kinetic energy that just kind of enters it and goes through it. What do we reckon? Great, so they're asking about kinetic energy. So this must have something. This must have something to do with the formula 1/2 mv squared. That is the kinetic energy after all. So kinetic energy of some body is the mass times the velocity squared. We're interested in the air that will have entered. So what is the mass of air that will have entered and what is the velocity of that air? So we know the mass of air that would pass through in this time. In this question here, what did we show? We showed that the mass of air that would pass through the blades each second is about this much here, in fact. Calculate the kinetic energy of the air entering each second. Okay, so we've got the right mass. 1/2 of 4.2 times 10 to the 5. And what's the velocity? Great. Yeah, I'm seeing some really good answers here. Nice. The velocity is equal to 11 meters per second. And we need to square that. So if we plug all of this into our calculator, we should get around 2.5 times 10 to the 7 joules. Okay, does everyone get something roughly like that? Good. Okay, good. Right, then we have another question. It has been predicted that the turbine would produce an electrical power output of 10 megawatts in these wind conditions. Calculate the percentage efficiency of the turbine in converting this kinetic energy into electrical energy. So how do we find efficiency? This isn't something we've quite talked about yet. How do we define the efficiency in terms of powers or energies? Good, so efficiency is defined as the energy that we get out divided by the energy we put in. And that's a fraction, so that won't really be a percentage. To get from a fraction to a percentage, we multiply by 100. Okay. So, P out divided by power. Good. Okay, so what's the power that we're getting out of this thing? Right, so we could have chosen energy or we could have chosen power. So what's the power coming out? How much power are we actually getting out of this thing? Good, the electrical power output of this device is 10 megawatts. So the efficiency is equal to our 10 megawatts, which is 10 times 10 to the 6, divided by our input power. What's our input power? What is power? The definition of power is energy per time, or the amount of energy per second. So how much energy per second is going into the turbine? Good. Yeah. 2.5 times 10 to the 7. We said here, okay, what's going into this thing? All that's going into this thing is kinetic energy. It's just the energy of the wind, which is just how fast it's moving. Good. Now, that's like energy going in, but we want to know power. Power is energy per time. But what we've actually found here is the kinetic energy that enters this device each second. Now, rather than saying each second, we could say per second. And the amount of energy per second, well, that is the power. Good, so what we've really calculated here is that the power input is 2.5 times 10 to the 7 watts. So we can use this in our calculation. The input is 2.5 times 10 to the 7. And then we have to multiply by 100. So if we chuck this into our calculators, what do we find? We should get 39%. Yeah, roughly 40%. Absolutely right. Good stuff. Fantastic. Well done. Okay, well, so this is finished up slightly shorter than usual. Usually I'm struggling to finish on time, so this is very unusual for me. But yeah, I guess we smashed through the questions. So well done, you guys, for getting your answers to me so quickly and confidently. Yeah, it was a really good session. Thanks. Thanks very much for Thanks very much for all your input and giving us all your answers and so on. Makes it easy for us to kind of see how it's going and check that you're getting it. Okay, so seeing as we've finished that section, I'm now going to do a little snap revise walkthrough for anyone who wants to see it. Yeah, you have a nice day too. Thank you very much, everyone, for coming. So like I said, there's a coupon at the end for anyone who wants to try out Snap Revise, where we're doing like loads more of these web classes at the moment. The idea is to kind of do tutoring, but a way more affordable price. So I'm going to do a little walkthrough, and at the end of that, I'll drop the coupon code if anyone wants to give it a try. So let's just set that up now. There we go. Sorry, just 1 second. I'll be with you in any second now. Great. Okay, fantastic. My apologies for that. Here we go. So just a little walkthrough of Snap Revise to show you what we've been up to, because I think it's pretty cool stuff. So I've logged into Snap Revise and I get sent straight to my dashboard where I have the various courses that I'm signed up for. So I've currently got A-level maths and A-level physics running on here. I'm going to take a look at A-level physics. So I'm going to go to the course. Now, the idea of the courses on Snap Revise is to try and streamline your learning. So in particular, so we've produced loads of really good resource materials for you to learn from. In particular, we've turned all of the major exam boards into video courses. So we've got video courses for AQA physics, for EdXL physics, and for OCR physics. That's the other one. But alongside the kind of learning materials, one of the big things we've been doing at the moment is trying to decrease the amount of time that you need to try and streamline the time that you spend to make sure that you're only learning stuff that's new to you, the stuff that you need to learn, and not spending time on things that you already know. So let's take a look at an example. So every course actually starts with a quiz. And we know loads of things kind of have quizzes on them, but the result of our quiz is really the important bit. So let's take a look at, we've got to look at work and energy. So let's see what we understand about work and energy now. And we may as well have a crack at these questions, seeing as we're doing the work and energy session. So, okay, a man pulls a cart with a force of 70 newtons. What is the distance covered by the cart if the work done by the man is 280? So distance, work done equals force times distance. So we need 280 divided by 70. So that's going to be 4 meters. Good. Okay. Let's take a look at another. A 1 kilogram block falls from a height of 10 meters under a gravitational field of this much. How much work did they do? So it should be, that's mgh. So that's 10 times 10, which is 100. Okay, now let's make sure we get a couple wrong. So good. Got that one right. Okay. Go. Wrong. Okay, so we got 50%. So here's where the good stuff happens. It doesn't just it does this bit where it tells us what we know and what we didn't, and maybe we could come away from this and we'd now know what to focus on. But how much better would it be if the course now was now made to fit around what you need to know and what you don't need to be focusing on? So we now go into the Snap Revise course, and it's highlighted for us everything that it wants us to take a look through. And it's highlighted for us everything it doesn't think that we need to right now. So for example, introduction to work done, we got the basics down. You see everything's highlighted in green here. However, there's this video in orange, calculating work done using constant force displacement graphs. Okay, so we got this question wrong, a question that involved a graph of force against distance. Here we needed to know that we needed to find an area under the graph, but we got that one wrong. So SnapRevise knows we need to do this bit of the course. So it sets us up on the video course, and it highlights all the bits in orange that we need to watch. So again, we got this bit correct, so that's all good. Let's take a look at another one of the videos. So here again, all highlighted in orange. And same here. Good, okay. So aside from setting us up so that we streamline our learning and only spend our time on the stuff we need to know, or the stuff that we specifically would best spend our time working on, there's some extra stuff going on. So for example, we thought it would be better, rather than making some exam questions and giving the answers, we thought that a big problem with trying to get through exam questions is figuring out how you would actually figure out what the question means yourself. So we thought it would be a cool idea to do some videos at the end of each kind of mini section of the course, where we go through some exam questions ourselves and we explain how we would have got to the answer. So we think that's a bit more useful than, for example, just looking at a mark scheme for an exam question where the answer kind of pops out of thin air. Once you've seen an answer, it might make sense, but you kind of wonder how you'd have got to it. So at the end, there'll be some more quizzes to check how we've gotten on and how much we've improved from the start. So it's good kind of bite-sized chunks to work in as well. Idea is that hopefully it'll be like a bit less overwhelming as well. Looking at the whole course at once feels like a lot. So we've been working on exam packs and revision guides. It's just extra materials that we think would be useful for you to learn from. And then so we'll give you an idea of the plans. So our idea is, especially with this kind of web class end of things, our idea is to kind of take private tutoring and turn it into something more accessible and more affordable than private tutoring is. So tutors can cost up to £50 an hour. And we're thinking, what can we do? What can we do instead to kind of improve on this situation? So we thought we can try and provide the private tutor style experience at a fraction of the cost. And so that's the ultimate package. Now, so first of all, I'll mention the basic package. So for the basic package, you'll have access to all of our learning resources, and that's for just £10 a month. Now, if you're interested in this smart adaptive learning stuff, where we want to try and help you streamline your learning, then access to that part is in part of the Pro plan, which is £30 a month. And here, not only do we have all of these self-marking quizzes, etc., we also have things called predicted exam packs. So we try and come up with these packs of exam questions, which we think are the sort of things that are likely to come up in exams, etc. Just our guess of kind of interesting exam questions to look at. Finally, there is the ultimate section. So here the idea is to really kind of get as much of the private tutor experience as possible. Private tutor could be around £50 an hour. So we thought, what if we charged that much for a month and then did as many sessions as we could in that month? So right now I'm doing loads of web classes every week. I do a couple on YouTube, but I do more on SnapRevise itself. And well, in fact, at the moment, because of the current situation with schools being closed, I'm redoing quite a lot of sessions. There's actually 6 sessions a week on SnapRevise at the moment. Usually there's 3 or 4. So what else do we want to say? Great. So the idea of the web classes, it's kind of like this. Some of them I go through some material and we discuss it together. A couple of them are drop-in tutor sessions. So here you can come in with any questions, any problems that you have. So in particular, if there's an exam question you're stuck on, or if there's just a particular concept you just can't get your head around, bring it to the session, and then I'll talk about it with everyone and we'll work through it as a group. So I'm running those kind of sessions as well. Sorry. Yeah, and so I'd love to see some of you at some future YouTube sessions, and hopefully some of you in the SnapRevise web class sessions as well, where we're doing even more of this stuff. Cool. So I'll just stop the share there and bring us back to the slideshow so you can see the coupon section. So here's some upcoming study clubs. So set yourself a reminder. We'd love to see you there. And finally, there is the coupon for today. So thanks very much, everyone, for coming. Yeah, thank you very much for sticking around and listening. See you guys in the coming sessions. Bye. Thanks very much. Cool. I think if that's all, then I'll sign out there for today. Thanks very much, everyone, for coming, and see you all in the future. Good to see some good and old faces, as always. Well, handles. Well, do let me know if you have any questions. Okay, I think if that's all, then we'll leave that there. Thanks so much, and see you all in the future. Bye. Yeah, stay safe. Okay, thanks very much, everyone. Bye.